Hello, welcome everyone. Uh, today I'm going to tell you about the flaws in our understanding of general relativity. I am Rohit, and this is my YouTube channel, and I am basically the author of this book, Decoding Gravity, Time, and Causality, Rohit Kale. And this is basically describing the new theory of quantum gravity and potential theory of everything. So this is going to be I think, a big thing in physics. So whoever is basically interested in understanding the new theory of everything in town, I would recommend to buy this book. It will be available internationally soon, and also I will be telling you about this theory, a few aspects or few secrets of this theory in this YouTube channel. So I recommend that you subscribe it, and you also share with people who might be interested. You don't need to be a physicist or a physics expert or PhD holder in physics to understand this book. So you can actually, even if you have some basic understanding of quantum mechanics and general relativity, you will be able to understand this book. This basically does not have any complex mathematics, and it is not, it's a phenomenological description. So it's basically logic based. So it's not some hi-fi theoretical book, but it is a very practical kind of a book. Anyhow, without further ado, today I'm going to talk only about general relativity. So the theory which is described in this book is called as dynamic general relativity, which is basically general relativity redefined. But today we are going to talk only about general relativity, which was given by Einstein in 1915. So we will basically, before we go into what are the potential flaws, which I think are pretty interesting flaws in our understanding. I'm not saying that general relativity is wrong. We don't understand general relativity well. What exactly is general relativity trying to tell us? Since 1915, we are not able to understand that. So I'll just first go into what general relativity is. General relativity is basically a theory of gravity described by Einstein. Okay, so it says that, you know, the gravitational interaction, it travels with a gravitational wave. So a gravitational wave starts from the Earth and it goes with speed of light outwards. Okay, so if the Earth is spherical, the logical conclusion is that the wave will also be spherical wave. So spherical gravitational wave which starts from the Earth and it goes with speed of light outwards. And this basically, so the mass of the Earth tells the fabric of space-time, okay, how to bend. Okay, so the mass is telling how much to bend, how much not, how much to bend. So the farther it goes, the farther lesser the fabric of space bends. Now here again, basically it's the general relativity says that it is the fabric of space-time which bends, basically just like a trampoline. So this trampoline analogy is very commonly given. This trampoline analogy, I know physicists keep saying that you should not overdo the trampoline anomaly because trampoline is a 2D and what we are talking about is 3D. The space-time is 3D, so there is no surface on it. So a deformation or a geodesic is formed on a two-dimensional surface, but it's not on a three-dimensional. So it's a and this is very good analogy for describing how the Earth moves around in spheres, but it's very difficult to extrapolate the same changes in the shape to explain the falling apple. So how exactly the space-time changes are occurring to to explain what is a falling apple. So it is a very difficult thing, and often the physicists give this argument that basically the changes in space-time is very difficult for a layman to imagine. So anyhow, so these are the so basically this is a geodesic, which is a two-dimensional, and we are talking about three-dimensional. Unfortunately, I'm going to despite physicists saying that you should not overanalyze these changes, because it's very difficult for us to imagine, but I'm still going to do that today. I'm sorry for that. And before that, I'm very sorry about the lightning and all, because I'm doing this at home, so lightning part is a bit poor, and also probably microphone is also poor, but I think that you'll get the idea. So this I'll just explain to you with this particular figure. E is the Earth, basically. Okay, so we are basically interested in these 2 points P and Q, which are at a distance from the center of the Earth. They are same distance from the center of the Earth. Just imagine about h height from the surface of the Earth. So what we are interested in is what is going to happen to the space in between P and Q. So we know that the gravity of the Earth, basically the mass of the Earth, causes gravitational time dilation, and there is maximum gravitational time dilation nearer the surface, and as we go far, there will be lesser and lesser and lesser gravitational time dilation. But we know that yes, between P and Q, whatever space is there will be some gravitational time dilation, and also space will contract over there. So we know that P and Q are going to contract, but it's not instantaneous. So we know that a gravitational wave starts. It starts from here, and it keeps going with the speed of light. As it reaches P and Q, it gives the information is transferred basically with the speed of light. So it will take some time for the gravitational wave to start and reach P and Q. Now there comes a problem basically. Once it reaches P and Q, what next? It will basically tell the time over there to reset, and it will also tell the space over there to contract. So okay, space will contract, and this will cause the change in the shape of the geodesic, which was described by Einstein. Anyhow, that is okay. Now what next? So the question is it a single wave which comes, or there are multiple waves? So the answer is pretty simple. It's pretty obvious that there cannot be a single wave. So it has to be multiple waves. So then the question comes that let's number these waves. So first wave we number as 1, then second wave we number as 2, and third wave 3 and 4 and 5, like that. So the next question which comes to an obvious mind is that, okay, so what is the duration between these two waves? That is, the first wave comes, and after that, after how much time the second wave comes, and then after that, how much time third wave comes. So there are basically two possibilities. First possibility is, okay, so Earth is not a static body. Basically, it keeps moving. It keeps on moving with a very high speed in the space, but the speed of Earth is extremely less as compared to the speed of light, so we can basically ignore it for some time. But even then, so there are two basic possibilities. Now I am not aware of what exactly the two. You can in the comment section you can tell me what is the real thing. But yes, E. So the second gravitational wave might start after the Earth has moved. So that is one possibility. So Earth is static, and the gravitational wave starts, and then Earth moves, and then the second position of the Earth, again another gravitational wave starts, and the third position of the Earth, again the gravitational wave starts. So which means that the distance between the gravitational waves basically is basically determined by the velocity of the Earth, or for that matter, any object which has gravity. So this is one possibility. I don't know whether this is the right possibility or not, but whatever it is, I don't think that this is the right answer. Okay, so let's imagine that there is x waves per minute. It starts x. This is just random one figure. You can imagine any random figure, maybe 1 nanometer or 2 nanometers, 10 nanometers is the difference between first wave and the second wave, the time difference. The third question which will be asked is what time, because there are so many times over here. So as soon as we go just above the surface of the Earth, there'll be one time with one particular time, gravitational time dilation. Then we go further up, there'll be another gravitational time dilation. Then again third and fourth and fifth. So there are as many number of such time zones which we can imagine. That many number of times are there. So if we want to basically analyze these gravitational waves, so how much time per wave in 1 minute, how many waves are coming? This we have to measure with which time? We don't know. So there is no concept of universal time. Actually, there is one concept in general relativity which is called as a T0. T0 is what? The time of an observer which is at infinite distance from the Earth, which is basically similar to universal time in DGR. I will come to that in the next video when I describe time. But so you have to. So we'll just come back to our 2 points, P and Q. So actually, there are not only 2 points here. Basically, these P and Q. I pardon this image. Actually, this is drawn by me. It's not very good, very accurate. It's drawn on paint. So there are not 2 points, but multiple points. So P can be anywhere. P can be here. P can be here. P can be here. Q can be here. Q can be here. So P and Q can be here. P and Q can be here. P and Q can be here. So there could be thousands or millions or billions or quadrillions of points around this which are equidistant from the center, and basically they form a sphere or circle or sphere around the Earth. Now, if you want to imagine what happens to the space between P and Q, so you draw a line between P and Q. So each of these millions of points, P and Q, you draw a line. And we know that the gravitational wave which starts from the Earth's surface, basically it is reaching all these points at the same time because it's moving at speed of light. So all these PQs will start contracting, which basically each and every of these points, these lines basically represents the surface of a sphere, basically. So this sphere will contract. So its surface area will reduce. Here in this figure, actually, I have drawn 2 spheres, and there is you can say there is a small space in between these 2 spheres. So these 2 spheres are incorporating a small volume. So let's say it is 1 meter or maybe 1 centimeter or maybe 1 millimeter, whatever you want. So there's 1 millimeter distance between these two outer and inner squares, and this P and Q are basically situated in that particular small thin volume of space. So what exactly happens in this space is that there is active the space basically contracts, but space, it doesn't contract only between P and Q, it contracts between every potential P and Q, which means that the whole sphere is basically contracting. Now, okay, it contracts. Now, how much it contracts? It all depends on the mass of the Earth. So the mass of the Earth is telling this particular sphere, depending on the distance, how much to contract. So that's what is given by the equations of general relativity. So okay, now this happens with the first wave. So what about the second wave? Then the second wave reaches. Then the second wave again also does the same thing with P and Q. It the whole basically it does the same thing with all the potential P and Qs all around this thin spherical shaped volume of sphere. So all this spherical shaped volume will contract. So it will contract, and then again third wave will come, and then third wave will also give the information to contract. So basically what is happening is so here this whole sphere will basically reduce in size, and it will lose. So both these spheres actually will lose surface area, and this whole sphere will lose volume. So it will lose volume basically because the space in between them is contracting. The space is contracting, that means the volume in the space is reduced. So this volume, the surfaces of each of these two spheres will reduce in surface area, and the volume in between the two will also be reduced as the second wave reaches, and then the third wave, and the fourth wave. So what will basically happen is that this whole volume, so if you can see here, this is not this figure is not reducing. It's only this outer sphere which is reducing. The Earth is remaining approximately the same size, and this whole sphere is contracting. The sphere is again contracting. So you can see that the sphere keeps coming down, keeps coming down. Now this is the unfortunate thing is that general relativity is never basically described in this manner. I don't know why. But I've not seen a single physics book. I've seen one YouTube. There was one person, I don't know the name, but there was an animation, and that was a very good animation which shows very similar thing. So basically, okay. So this is only one cubical volume of, spherical volume of space. So there are multiple millions, billions, quadrillions, quintillions of potential spherical volumes of space all around the Earth. Each of the, whatever arguments we have made till now, they basically apply to each of these. So basically, any spherical volume around the Earth will basically contract, keep contracting, and the P and Q will start. So basically, as you can see that not only P and Q are going towards each other, but they are also going towards the center of the Earth. And again, as the distance between P and Q reduces further, the distance between P and E, that is the center of the Earth, and Q and the center of the Earth is also reducing. So this whole sphere is going down. Now, if you can imagine that there is a light ray which is coming from this side. So as soon as it reaches here, this sphere goes down. So the light ray will be deflected downwards because the space is contracting downwards, so it will pull the light ray downwards. So this explains very nicely gravitational time dilation. Even gravitational redshift can be explained. So if there is a light which is going in this direction, so you can imagine two photons which are basically subsequent photons. So first photon goes and second photon goes. So the space in between the two, the first photon will be pulled much less than the second photon, which means that the distance between these two photons will increase basically. So that's basically gravitational redshift. So even gravitational redshift can be explained very nicely with this. And we are talking only about general relativity. We are not talking about special relativity as yet. So so this is what is the potential flaw which we have about general relativity. Now, in the next YouTube video, I'm going to talk about what is a potential flaw in our understanding of time. So I would recommend that you people share this video more and subscribe. And if you want to know more about DGR, you can buy the book. Thank you very much.